So the problem we had is we got our brand new research vehicle with the name Edgar that you can see on the right-hand side. And we wanted to take this vehicle to drive fully autonomous around Munich. So first of all, of course, we needed some kind of base software where we ended up with Autoware because it provides a really nice software stack. But the main problem we were facing is that it's really hard to get the vehicle out in the real world, because Autoware works quite well with the sample maps, but it does not really provide a whole pipeline to create HD maps that can be used directly with the software. So we want to provide a better pipeline for HD mapping to be actually able to bring Autoware out in public traffic. So first, we looked into what we need, and we defined some kind of requirements. Basically, what we want to have is a whole pipeline from raw sensory data to full HD maps, meaning we need both a PCD map and also a Lanelet 2 map. And we want to use this map online for localization, but also for tasks like motion planning, motion prediction, and so on. So what is there already? There are some kind of LiDAR mapping algorithms or SLAM algorithms, but unfortunately, most of them do not include any GPS data. And also, we were facing lots of problems building consistent PCD maps with our unconventional sensor setup. Then we also can use the vector map builder to manually build HD maps based on PCD maps. And what we also want to use is, of course, the online localization pipeline from the Autoware software stack. So the missing pieces that we saw in the whole process is, first of all, a georeferencing. As I already said, even if we can create consistent PCD maps, usually they are not georeferenced, as many of the algorithms do not include GPS signals during the mapping. So we want to georeference both the PCD maps and also the Lanelet 2 maps. We want to validate the whole thing based on real-world scenarios. And of course, one really important thing for us is the scalability, to not have tons of manual processes each time we want to create new maps, but we want to have a process that really scales well into new regions and scenarios. So we tried to address all of these problems with our new tool, FlexMap Fusion. So what do we want to do? Basically, we want to use the advantages of SD maps, namely OpenStreetMaps, which is community-based. And the community really manages to have great maps there, lots of really recent information. And we want to bring this together with the information that we can create and we can map with our research vehicle, Edgar. Fuse all of this together and get nice HD maps that we can use within the Autoware software stack. So how does the mapping process look like? As I already said, first of all, we have to create PCD maps. Therefore, we use our custom version of the KISS ICP that fuses all of the LiDARs together to get consistent PCD maps, as you can see on the right-hand side here. We also have RTK-corrected GPS, meaning that where GPS is available, we have quite high information about the actual traveled trajectory of our vehicle. Then we can use the vector map builder tool to create vector maps, Lanelet 2 maps for the created PCD map. And we also have some kind of online information from OpenStreetMaps. The big question we were wondering is, how can we get all of this information together in a really smart way? And the answer we came up with is exactly our tool, the FlexMap Fusion. As we were quite busy with the implementation so far, we don't have a fancy logo, so you have to use your imagination here. This is how the tool basically looks like, integrated into our whole offline mapping pipeline. So we can create with the LiDAR sensors, we can create point cloud maps. And as I already said, we also have the Lanelet 2 maps and the FlexMap Fusion tool. brings all of this together with the goal of having a georeferenced lane-led 2 map that is enriched with features from OSM and also a georeferenced PCD map. And this is basically done in 3 steps: the map alignment, map conflation, and georeferencing. And in the next few slides, I want to show how these 3 steps work. So let's first start with the map alignment. The problem we basically have is we have 4 different kinds of information. So we have the lane-led 2 map, which is in the same coordinate frame as the SLAM trajectory, as the lane-led 2 map was created using the PCD maps. And then we have the OpenStreetMaps, which are in the same coordinate frame as the GPS. So we have 2 different coordinate frames that we want to bring together, and we also have different representations of the OSM and the lane-led 2 that we also somehow want to combine together to make it possible to transfer information from OSM into our lane-led 2 map. So in the first step, we want to align the maps. As you can see on the right here, this is how the result looks like after doing the UTM projection of our SLAM trajectory and running a rigid Umeyama transformation between the GPS trajectory and our SLAM trajectory. The problem is, since it's a rigid transformation, it cannot really change things in the SLAM trajectory, meaning that the drift that occurred during the mapping cannot really be compensated for. Therefore, we need the next step, and here we applied a rubber sheet transformation algorithm. The rubber sheet transformation algorithm defines several control points along the trajectories, which can be either created manually from, as you can see in the image here, for example, from 90-degree turns, or also from GPS when GPS is available. And what the tool does is it triangulates basically the whole region around the trajectory, and within each of these triangles we have linear transformations, and the rubber sheet algorithm makes sure that everything is consistent on the borders between those triangles. Here you can see the result, how it looks like. As you can see, both of the trajectories now align really well. The only region where this is not really the case is here around the middle of the trajectory. But the problem here was that just the GPS was not really available. That's why we see quite higher deviation here. So we have now 2 aligned maps. The question is, how can we conflate it, meaning how can we transfer information from the OpenStreetMaps into our local HD map? And therefore, as you can see here, the problem is that, for example, this T-crossing looks different in the OSM representation than it does in our lane-led 2 representation. So we created some algorithms to bring them into a common representation. And this allows us to try to find the correspondences between the OSM and the lane-led 2 maps. This is done by using a buffer growing algorithm. And the buffer growing basically uses our lane-led 2, or the collapsed lane-led 2, walks along this and builds some kind of buffers between the connections between these nodes, as you can see here. And within each of these buffers, the algorithm now tries to find matches between the OSM and the lane-led 2. And then we know these correspondences. And here you can see how this looks like in our tool. So what do we actually want to do with this information? As you can see here, for example, there's a lot of information included within OpenStreetMaps that we have thanks to the community that do the mapping for OSM. However, it's really hard to extract this information from online sensory data. For example, it's really hard to get the speed limits for the HD maps. But with our tool, it's really easy, as we can just take the information from the OpenStreetMaps and transfer it into our HD map. The next step is the georeferencing. And the nice thing here is that we can, with our tool, we can georeference both. We can georeference PCD maps and also lane-led 2 maps. And it's implemented quite easily. So even if you do not want to run this whole pipeline here, but if you have just GPS data and your PCD map, and you somehow want to align them, you can also do this with our tool without having to deal with any lanelet 2 or HD maps. We are still trying to figure out what's the best way to really validate the results. What we came up with is we use some kind of orthogonal photos that we can get from the Bavarian state. And we have done some kind of evaluations with this, and we can say that it really looks quite well. However, there's still more evaluation ongoing on how well this actually works, and also how well it generalizes for other regions, as we really want to drive all around Munich autonomously. So what's the current status of our project? We do have a running implementation. The code is already up on GitHub, is open source. It's a standalone Rust2 C++ package that can be integrated with Autoware quite easily. So in our institute, we are running it in a full Autoware setup. However, for the open source, we try to remove the dependencies to Autoware so everyone can use it. And the nice thing is it basically runs on any standard consumer notebook. So no need for really high performance machines. What is missing? First of all, we want to have a better integration into the whole mapping pipeline, so making it easy for basically any research team around the world to create their own HD maps, and not only use our tool, but have a better integration with the whole process of PCD mapping and so on. And currently, we're working on an automatic tool to create lanelet tool maps based on OSM. So we do not need this manual vector map builder step, but we only need the vector map builder to kind of refine these OSM maps. So why do we think FlexMap Fusion is well candidate for the Autoware challenge? We think, or actually we are sure, that there are many benefits of how the Autoware software stack can benefit from the FlexMap Fusion tool. We found out that for us, the mapping was a big obstacle to bring Autoware actually out on public roads. And with FlexMap Fusion, this step is easier. The package is easily usable for everybody. So we implemented it in a way we provide some test data for everybody. It's already up on GitHub, and everyone can use it on his own laptop. This makes it also expandable with multiple more features. As I just showed, there are some features that we are currently working on, but we are also happy if the community can provide some other features. And we implemented the software in a way that it's easy for everyone to contribute new features to the software. And last but not least, our software is independent of the target vehicle, meaning that no matter with what vehicle you recorded the data, you can always use our tool and benefit from it. So that's it. I want to give a really short recap on the FlexMap Fusion. FlexMap Fusion supports the whole HD mapping tool by leveraging different sources. It allows to fuse the SLAM, the GPS, OSM, and lanelet 2 trajectories in a smart way. And the tool is already available on GitHub. So here you can see a small QR code. Check out the code. We're happy to receive some feedback, to receive some pull requests, and we're happy if someone is working with our code. Thank you.